color photograph shows several computer monitors with blue error screens. Figure 6.1 operating systems operate on many computers and devices, which means that when they need an update due to an error or virus, all those systems need the same fix. Credit modification of Windows blue screen on room full of computers by grj23/Wikimedia, com, cc0. Chapter Outline 6.1 What is an operating system? 6.2 Fundamental OS concepts. 6.3 Processes and concurrency. 6.4 Memory management. 6.5 File systems. 6.6 Reliability and security. TechWorks is a startup company that is 100% committed to leveraging innovative technologies as part of its repeatable business model and as a business growth facilitator. TechWorks has been suffering for many months from the limitations of its operating system, especially the system's lack of security, which allows access to unauthorized and unauthenticated users. This problem reflects poorly on the company's reputation. To address the security limitations, one of the company's project managers decides to implement a new mode of protection that supports all of the operating systems the company's users use, including iOS, Windows, Linux, macOS, and Android. A data scientist working for the company proposes two solutions. The first solution involves integrating an authorization method called two-factor authentication, which you'll learn more about later in the chapter. This method adds another level of security by asking users for their cell phone number so that it can send a one-time code to verify their identity every time they try to log in using their username and password. The second solution involves adding a table that defines individual user privileges such as read R, write W, and execute E. This solution regulates access by leveraging features that were already part of TechWorks' operating system. One of the core features of an operating system is to manage and regulate access to the program components that are running on various machines. This is particularly important today as the program components that power modern solutions, e.g., advanced robotics, autonomous cars, and drones, are typically distributed across many different machines that communicate with each other to perform various functions. To ensure the security of such systems, a single sign-on capability is typically required to facilitate access to all the components involved. Learning objectives. By the end of this section, you will be able to describe an operating system and its role in computing. Explain the architecture of operating systems. An operating system, OS, is the core piece of software that typically manages and controls the interconnection of hardware and software on a computer. The OS is loaded upon startup and is the key piece of software needed to operate any computerized device. Introduction. There are many operating systems, OSs, and anyone using a modern computer is using one of them. The typical OSs for computers are Windows, macOS, and Linux, and for mobile devices, iOS and Android, Figure 6.2. Microsoft Windows is a popular operating system, celebrated for its ease of use and broad software compatibility. Apple Inc.'s macOS, which is the driving force behind Apple computers, ensures tight hardware-software cohesion. Linux, a freely available open-source OS, is acclaimed for its reliability, safety, and adaptability. Linux source code has over 27 million lines of C, while Windows has over 50 million lines. Linux offers a variety of versions or distributions, such as Ubuntu for ease of use, Fedora for the latest features, Debian for stability, and Kali Linux for security tasks. Each version is designed to meet specific needs, from general computing to specialized applications. All the commercial operating systems today manage security for users. A diagram shows multiple users and devices running different operating systems, connecting securely to network. Figure 6.2 These days, organizations, such as companies and universities, must enable a variety of users using a variety of devices supported by a variety of operating systems to securely access their systems. Attribution, copyright Rice University, OpenStax, under CC BY 4.0 license. The goal of this section is to explain what an OS is. Traditionally, we think of the OS as the means by which communication between applications that the user wants to run and the computer hardware that is responsible for running them is facilitated. Applications typically do not directly manipulate the hardware. Instead, they must ask the OS to do this on their behalf. One of the primary goals of the OS from an application software point of view is isolation. Isolation ensures that the multiple programs that are running concurrently on the same CPU and memory operate independently without interfering with each other's execution or data. This maintains system stability and security. From a hardware point of view, the hardware is designed to enable programmers to write OSs and applications. In general, the OS mediates a program's access to hardware resources such as the CPU for computation, memory for volatile storage, and disk, flash memory, and so on for persistent storage, TCP/IP stacks, Wi-Fi and Ethernet network interface cards, and so forth for network communications, and keyboard, display, touchscreen, audio, game controllers, and so on for input-output. Isolation is what allows device manufacturers to update their hardware without requiring software developers to rewrite their programs each time. Link to learning. To learn more about operating systems, read this informative article on understanding operating systems from How to Geek, Monitoring Access. Operating systems play a crucial role in managing and controlling access to hardware devices within computer systems, including peripherals such as keyboards, mice, hard drives, and other critical components. They act as gatekeepers, ensuring that interactions with these devices occur smoothly and securely. One of the key responsibilities of an OS is monitoring hardware access, which involves tracking and regulating which applications or users can communicate with the hardware and how they do so. This capability is vital for maintaining a system's overall integrity and performance. In addition to hardware monitoring, the OS is instrumental in enforcing authentication mechanisms. This means the OS helps verify that only authorized users gain access to certain devices, especially those considered sensitive. By managing user permissions and access levels, the OS can prevent unauthorized access to critical hardware resources, safeguarding against potential security breaches or data theft. This aspect of the OS is particularly important in environments where access to information and resources needs to be tightly controlled, such as in corporate or government settings. The role of an IT administrator is to define which hardware devices are available within a company's network and determine their sensitivity levels. This task requires a deep understanding of both the technical specifications of the hardware and the security implications of its use. You may be wondering, how is the OS organized? How are resources shared across users? How is one user or process protected from another? Such questions relate to the characteristics or properties that are considered when designing an OS. Table 6.1 depicts various OS design questions and the properties they are associated with, such as structure, sharing, naming, protection, security, performance, availability, and reliability, among others. Property question. Structure: how is the OS organized? Sharing: how are resources shared across users? Naming: how are resources named, and what is the scope? Protection: how is one user or process protected from another? Security: how is the integrity of the OS and its resources ensured? Performance: how does an OS avoid making all the applications run slowly? Availability: can the applications always access the services they need? Reliability: how often do things go wrong either with the hardware or with a program? Extensibility: can new features be added? Communication: how do programs exchange information, including across a network? Concurrency: how are simultaneous activities, such as computation and I/O, created and controlled? Scale: what happens as demands or resources increase? Persistence: how can data be made to last longer than program executions? Distribution: how can a computation be allowed to span hardware, such as machine network boundaries? Accounting: how can a user's resource usage of an OS be tracked, and how might the user be charged for it? Auditing: can actions and processes be reconstructed? Table 6.1 Operating System Design Considerations. Efficiency management. By managing system resources, e.g., CPU, memory, disk, and network, efficiently, the OS ensures that no resource is underutilized or overburdened. We start with this question: what level of ease or complexity is involved in developing applications with optimal efficiency on a computer? A well-performing operating system facilitates the development of efficient applications that enhance the user experience by providing faster response times. The OS also impacts user experience positively by managing resource allocation and multitasking efficiently. At some point, you might work for an organization that is engaged in developing a new app, and the company may ask itself this question: if we were to take the time to develop all the additional software required for our application to boot and run on raw hardware, how much faster would it be? This is the same as asking what the penalty or cost is of developing what the OS provides, i.e., sharing of the hardware among apps, and limited damage when programs have defects? The answer to this question relates to runtime efficiency. With respect to coding time efficiency, the OS includes various abstractions, interface, and libraries that application programmers can use to ease the burden of software development. Having to write these from scratch without the support of an operating system would greatly increase the required coding effort and extend the development time associated with application development. Mechanisms implementation. In operating systems, a policy is a way to choose which activities to perform, i.e., what needs to be done, and a mechanism is an activity that enforces policies, i.e., how to do it, which often depend on the hardware on which the operating system runs. If a process is granted resources using the first-come, first-served policy, then that policy may be implemented using a queue of requests. To understand how policies and mechanisms relate, consider this analogy. A car is a mechanism because it enables operations such as going, stopping, and turning that enable a driver to get from point A to point B. Notice that the mechanism, in this case, the car, does not say anything about how to use the mechanism to get anywhere in particular. The driver provides a policy by deciding on a route. Now compare a car with a public bus. In this case, the bus driver determines the policy. The same goes for the self-driving cars that are being developed these days. They serve as the mechanism, as there are no decisions about routes being built into cars. Instead, a self-driving car uses machine learning to determine a policy, which includes deciding on a route, selecting the procedure on how to drive, and allowing the driver to override automated driving at any time. OS level and server virtualization. The ability of a system or server to run different types of applications used by multiple users at a time on the same computer is called virtualization. Server virtualization places a software layer called a hypervisor, i.e., virtual machine monitor, or VMM, between a machine's, i.e., servers, hardware, and the operating systems that run on it. The hypervisor creates and manages virtual machines. A virtual machine, VM, is software that is created to run like a physical computer, and that operates its operating system and applications like separate physical servers. OS-level virtualization is a basic form of server virtualization. When using OS-level virtualization, there is no need for a hypervisor, as the server's OS handles all resources. Cloud computing leverages server virtualization and makes it possible for users to commission virtual machines. In this case, the servers reside in distributed data centers provided by cloud vendors. Commissioning a virtual machine is equivalent to gaining access to a virtual computer that runs a chosen operating system while leasing the underlying hardware and only paying per use, i.e., cost of CPU, storage, and network usage, OS architecture and support layers. As you've now learned, the OS is a system software program whose job it is to manage all the programs running on a computer. OSs enable users to run multiple applications at the same time and keep them from interfering with or crashing each other. OSs provide convenient abstractions to handle diverse hardware. They coordinate resources and protect users from each other using a few critical hardware mechanisms. OSs make it easier for developers to create applications by offering built-in features that help with managing errors. These features include fault containment, which prevents errors in one part of an application from affecting the whole system, fault tolerance, which allows the application to keep running even when errors occur, and fault recovery, which helps the system to fix itself or revert to a previous state after an error. The fact that these standard services are provided by the OS means that developers do not have to build these error management features from scratch, which simplifies the development process. Figure 6.3 shows the support layers within the Unix-Linux system structure. The OS navigates between three layers: the user mode, where the application resides; the kernel mode, which is in effect sandwiched between the user and hardware; and the hardware, which refers to resources such as the CPU and memory. In the next sections, we will describe these modes and the features they support in detail. A table diagram showing the system structure of a Unix-Linux system. It includes user mode, kernel mode, and hardware. Figure 6.3. The Unix-Linux system structure is made up of three main parts. 1. The user mode, 2. The kernel mode, and 3. The hardware. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Link to learning. Now that you've been introduced to the basics of operating systems, it may come as no surprise to you that operating systems come in all shapes and sizes. There are many different types of OSs, from batch operating systems to network operating systems, and each type handles many different functions, from file management to device management. This OS tutorial explains the different types. As you read along, consider how much you interact with an OS over the course of a single day, or how many different OSs you interact with. OS kernel features. The kernel is the program that is running at all times on the computer and provides basic services for all parts of the OS. Typically, the kernel is not the only program that is running. There is usually either a system program operating system or an application program running as well. Any program running on top of the OS is considered to be a process from the OS standpoint. It includes the program code, its current activity represented by the program counter, and a set of resources like open files and allocated memory. It also consists of address space, one or more threads of control executing in that address space, and an additional system state associated with it. The operating system uses processes to manage the execution of programs, ensuring they have the necessary resources while keeping them separate from each other to prevent interference. Software applications have to be compiled and linked with system libraries before they can run as executable programs on a machine. Each running program runs in its own process, and the OS can run, switch, and isolate processes from each other even though they are actually running on the same hardware. For a given application, the machine is the process abstraction provided by the OS. Processes provide user-friendly interfaces rather than raw hardware and an execution environment with restricted rights controlled by the OS. An OS virtualizes the machine by providing easy-to-use abstractions of physical resources while masking limitations. In this context, a thread is a path of execution within a process, and a process may contain multiple threads. Thus, multithreading involves executing multiple threads, i.e., execution units that are part of a process and share the same resources, concurrently, which improves overall responsiveness and efficiency. Industry spotlight. Operating systems and healthcare. In the fast-moving world of IT, it is crucial to think globally. This global perspective can be particularly useful when considering how IT and OSs affect healthcare. Namely, it can help us understand the role of OSs in patient care, medical research, and the efforts being made to make healthcare more widely accessible. The challenges associated with data sharing, privacy, and healthcare disparities impact regions around the world differently. As the delivery of healthcare becomes more integrated with technology, the choices made in designing how healthcare IT systems use OSs can significantly impact people's lives across the globe. These choices range from deciding how to take ethical considerations into account when using AI for diagnosis to creating IT solutions that respect cultural differences. Check out these initiatives from the World Health Organization and Centers for Disease Control and Prevention for examples in the healthcare industry. Imagine you're considering entering the healthcare IT field. Can you think of some ways that thinking globally and understanding the capabilities provided by OSs could improve your ability to solve problems and create solutions that work well for healthcare systems in various countries? Hardware management. The ISA defines how the CPU is controlled by the software by abstracting the hardware details from the applications. The OS provides an abstract machine interface to the application programs and leverages the physical machine interface to do so. The OS communicates with input-output, I/O hardware using device drivers, I/O ports, interrupts, direct memory access, DMA, and effective I/O scheduling. It provides abstractions to manipulate files, i.e., streams, and send messages to the network, i.e., sockets. Programming languages provide application programming interfaces, APIs that leverage these abstractions, e.g., file I/O, socket libraries, and related APIs, so that the application program can access the underlying resources that are managed by the OS. One of the main responsibilities of the OS is to isolate hardware from programs by providing common services and background management functionality, for example, Storage Manager, Network Manager, and Power Manager. The OS is the only system that should be able to directly access I/O devices, i.e., disks, network cards, and manipulate memory. Moreover, the CPU hardware provides a privileged instruction that can only be executed by the OS. The OS can use these instructions to establish an execution environment that limits access to, for example, memory. The application cannot remove the restrictions because it must execute privileged instructions to do so. Certain operations are prohibited when running in user mode, such as changing the page table pointer, i.e., the pointers to memory pages that are cached for faster access, disabling interrupts, i.e., the interrupts that the OS received from I/O devices, interacting directly with hardware and writing to kernel memory. Carefully controlled transitions between user mode and kernel mode include system calls, interrupts, and exceptions. The system call appears when the program requests a service from the kernel. The system interrupt manages the communication between the computer hardware and the system. The system throws an exception, which is an error that occurs at runtime. Then gets through. The ethics of open source OSs. The idea of making all operating systems open source, i.e., the copyright holder releases the content or product under a license that allows any user to access, modify, and distribute it freely, has both advantages and disadvantages. On the plus side, open source operating systems can be more secure and innovative because anyone can inspect and improve the code. This openness also encourages a global community of developers to collaborate, potentially leading to a technology that is more user-friendly and accessible for everyone. Additionally, openness aligns with ethical principles of transparency and freedom, as it allows users to understand and control their digital environments fully. There are, however, downsides too. Open source projects might struggle to secure consistent funding and professional support, which can lead to them having slower updates and fixes compared to commercial software. There's also the risk of fragmentation, where too many variations of the system can create compatibility issues and confuse users. From an ethical standpoint, the use of open-source operating systems globally can democratize access to technology, ensuring that no single company has too much control over our digital lives. It also encourages a culture of sharing and collaboration, which is essential for addressing global challenges like digital divide and ensuring equitable access to technology. However, the success of such a model depends on balancing openness with the need for sustainable development and support systems to keep the technology reliable and up to date. Should operating systems all be open source? Discuss pros and cons. Protected sharing. An OS's functions should guarantee protection, isolation, and the sharing of resources efficiently via resource allocation and communication. To implement protected sharing, the OS provides common services, e.g., sharing and authorization. There are many ways to leverage OS sharing. One involves the sharing of processors to perform computations concurrently. In this case, these computations will be completed as if only one processor had been allocated to them, although in reality, multiple processors are performing the computation's tasks in parallel. An OS also allows a computer's memory, input and output devices, and files to be shared within the tasks and the processes. It can also allow groups of computers to work together within the network and share resources. All of the sharing capabilities are controlled using secured channels. Learning objectives. By the end of this section, you will be able to explain various key concepts and components of operating systems. Discuss the various designs of operating systems. An OS manages computer resources, hardware, and provides services for computer programs, software. The OS works as an interface between the computer user and the system. The OS manages the memory, the files, the hardware, and the software. It also handles the inputs and the outputs such as the keyboard and printer, Figure 6. 4. A flow chart shows end user, arrows to and from software application, arrows to and from operating system, arrows to and from hardware, Figure 6. For the end user initiates this process by using the software applications, which are built on top of the operating system in the computer. Attribution, copyright Rice University, OpenStax, under CC by 40 license. In this module, we study OS components such as process management and threads, memory and address space management, and device drivers and I/O devices. In addition, we cover OS structures such as monolithic OS design, layered OS design, hardware abstraction layer, HAL, and microkernels, OS components. OS is a complex system that is typically created using the divide and conquer mechanism. That is, the system is divided into small pieces, each of which defines a part of the system. The OS component structure is static, and the OS and the hardware are tightly coupled together. The Application Programming Interface, API, is a set of rules and tools that allows different software applications to communicate with each other. Applications make requests to the OS through API. The user can, using a keyboard and/or mouse, interact with the OS through the OS interface. The OS interface could be a graphical user interface, GUI, which allows users to interact with electronic devices through graphical icons and visual indicators, e.g. Windows or a command line, e.g. DOS. For example, in Figure 6.5, the OS interface would be the window into which the Chrome browser opens. A diagram showing how the operating system and hardware are tightly linked. It shows the following user apps: Chrome, Photoshop, Acrobat Reader, JVM, application programming interfaces. File systems, memory manager, process manager, network support, device drivers, interrupt handlers, boot, and initialization. These are indicated as portable. Below these are layers of hardware abstraction and hardware CPU devices. Figure 6.5. The operating system and hardware are tightly linked. The end user is using multiple applications, such as Chrome, Photoshop, Acrobat, and JVM, which they had previously downloaded in a particular OS. To use these software programs, the user will interact through the OS interface and/or API, which is connected with OS components such as file systems, memory managers, process managers, network supports, device drivers, and interrupt handlers. Attribution, copyright Rice University, OpenStax, under CC BY 4.0 license. Process management and threads. With a single click, end users seamlessly launch applications, enjoying the simplicity of the process. Have you ever wondered what manages the application once it is launched? The direct answer is the OS. An OS executes many kinds of activities, starting from users' programs, background jobs or scripts, to system programs. There are many system programs such as print managers, name servers, and file servers. Each one of these programs or activities is encapsulated within a process. As you learned in the preceding section, a process is a running program that has an execution context plus the runtime instance of the program itself. Examples of an execution context are program counters, PCs, registers, VM maps, OS resources, and examples of runtime instance are code and data. Here are some other process-related concepts that will be introduced here and developed as the chapter progresses. A register is a high-speed memory storing unit. A process can be in running state when it is executed by the CPU, ready state when it is waiting in the CPU, or blocked state when it is waiting for an event to occur. The OS's process module manages the processes via creation, destruction, and scheduling. One way an OS controls access to a resource is through a data type called a semaphore. Managing the sharing of a system's resources to avoid interference and errors is called process synchronization. Think it through. Failure existence. Given the complexity of an OS's tasks, i.e., the management of a computer system's resources and the scheduling of tasks to make an application do what the user expects it to do, and the speed at which these tasks need to happen, it's amazing how often technology doesn't fail. But of course, it does at times. Let's suppose you ran into an OS-related failure this morning, namely, your laptop did not fully boot. What are some steps you would take to diagnose the problem on your own before seeking help or a repair? Processes versus threads. As we have learned, a process is an active program. A thread is a smaller or lightweight portion of a process that is managed independently. Table 6.2 shows a comparison between the process and the thread. Attribute process thread. Definition and executed program part of the process. Weight it could be heavy lightweight. Processing time more time less time. Resources needs more resources needs fewer resources. Sharing mostly isolated shares memory and data. Table 6.2 process versus thread. Processing. A program is passive. It is just bytes on a disk that encode instructions to be run. A process is an instance of a program being executed or processed by a processor. Thus, processing involves a program, a process, and a processor. The processor can be a real processor or a virtual processor, i.e., CPU core assigned to a virtual machine. At any time, there may be many processes running copies of the same program, e.g., an editor. Each process is separate and usually independent. An OS is responsible for managing these processes. Different OSs approach process management in different ways. For example, the Windows operating system's approach consists of adding an operating system call to create a process and other system calls for process operation. The approach used in the Unix OS is different from this, as it consists of splitting the process into two steps using fork and exec functionalities. The fork functionality is used to set up privileges by creating a complete copy of the process, and the exec functionality brings the executable file into memory to start the execution. Address space and memory space management. The address space is the set of addresses generated by programs as they reference instructions and data. The memory space holds the actual main memory locations that are directly addressable for processing. The OS is responsible for managing these memory and address spaces, Figure 6.6. To enhance performance, computers use virtual memory address space to create the illusion of a large and continuous block of memory for applications and the operating system to utilize. To do so, the computer's physical memory is used in combination with a portion of a hard drive that contains the swap file or page file. Pages containing address space information for programs are moved in and out of physical memory as necessary to ensure that there is enough physical memory to hold the pages of programs that are running at a given time. A diagram shows two columns, the first labeled address space, virtual, the second memory space, physical. Below the first is program A with an arrow to data X in the second column. Data X is also in the first column, but has no arrow. There is an arrow flowing from a blank part of the first column to program A in the second column, Figure 6. The addresses of the data will be in the address space, waiting for the execution to be moved to the memory space. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license. Computer memory consists of two main types, primary and secondary memory. The initial point of access for a processor that also serves as direct storage for the CPU is called primary memory. To be executed, programs must reside in primary memory. In multiprocessor systems, primary memory can be classified into three architectures. The first, Uniform Memory Access, UMA, employs a single memory controller, and thus, access time to any memory location is the same across all processors. The second, Non-Uniform Memory Access, NUMA, is a computer memory design that uses different memory controllers. Thus, its memory access time varies depending on the memory's location relative to a processor. The third, Cache-Only Memory Architecture, COMA, uses multiple interconnected processing nodes, each equipped with a processor, i.e., a cache. This allows for the dynamic allocation of data for optimized access and performance in multiprocessor environments. Memory that is used for long-term storage, housing the operating system, applications, and data that need to persist even when the power is off, is called secondary memory. Unlike primary memory, which is volatile and loses data during power interruptions, secondary memory is non-volatile, meaning it retains data even during power failures, and thus it provides durability and data retention. Common examples of secondary memory include hard disk drives, HDDs, and solid-state drives, SSDs. An OS must satisfy the policies of how much physical memory to allocate to each process and when to remove a process from memory. It must implement these policies using the following mechanisms: memory allocation and memory deallocation. Memory allocation is the process of setting aside sections of memory in a program to be used to store variables and instances of structures and classes. The memory allocation can be static memory allocation or dynamic memory allocation. Memory deallocation is the process of freeing the space corresponding to finished processes when that space is needed by the rest of the system. In addition, the OS must maintain mappings from virtual addresses to physical, i.e., page tables, and switch CPU context among address spaces. Industry Spotlight. Windowing systems. A windowing system is an OS software component that manages the display of graphical user interfaces, GUIs, on a computer screen. An investigation into the influence of windowing systems on various industries, particularly in sectors like retail marketing, has yielded insightful perspectives on how such systems impact business practices, productivity, customer engagement, and overall operational effectiveness. Namely, it's been found that windowing systems significantly enhance user experience, which is critical to retail marketing. By making it easier to integrate marketing messages or interruptions with other media that customers are watching, a windowing system helps retailers conduct targeted marketing over the internet. Windowing systems also improve the overall user experience for customers viewing the integrated content. Device drivers and I/O devices. Computers have many input and output devices, such as the keyboard, mouse, display, or USB port. Some examples of OS-specific devices include file system disk, sockets, network, and frame buffer video. A frame buffer is a portion of random access memory, RAM, containing a bitmap that drives a video display. A big chunk of the OS kernel deals with I/O, input-output. The OS provides a standard interface between programs, users, and devices to communicate with them, Figure 6.7. A device driver's routines interact directly with specific device types and related hardware to initialize the device, request I/O, and respond to interrupts or errors. An interrupt is a signal to the processor from either software or hardware that indicate events that needs immediate attention. Examples of device drivers include Ethernet card drivers, video card drivers, sound card drivers, and PCIe, Peripheral Component Interconnect Express, device drivers, which are associated with graphics cards and other peripherals. Device drivers are implemented by device manufacturers or open-source contributors and support a standard internal interface. They can execute in the OS address space and run at high privilege. A diagram showing various devices using device drivers connected to the operating system. The devices include a mouse, printer, drives, etc. Figure 6. 7 multiple I/O devices are typically connected to a computer. When the user starts using an application, the operating system will define the devices used by the application by using each device's driver. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Link to learning. Are your Windows drivers up to date? Check out to see if you have the latest drivers for your Microsoft devices. Device drivers are specialized software components that enable higher-level computer programs to interact with hardware devices. These drivers provide a software interface to hardware devices, allowing operating systems and other computer applications to access hardware functions without needing to know precise details about the hardware being used. At the heart of any computer is the CPU, the primary component responsible for executing instructions. Interestingly, CPUs themselves do not typically require external device drivers for direct operation, as the core management of CPU resources is a fundamental role of the operating system. Memory operates under the direct management of the operating system, which allocates and manages the system's memory resources. RAM can be accessed randomly and used for storing data temporarily while a computer is running. While standard RAM modules, both dynamic and static RAM, do not necessitate distinct drivers, specialized memory hardware, such as flash memory devices, including solid-state drives, SSDs, USB flash drives, and memory cards, interact with the system through file system drivers that manage the organization and access of stored data. Storage devices, encompassing a broad range of hardware from traditional hard disk drives, HDDs, to modern SSDs and removable storage media, require device drivers to facilitate data read-write operations. Network connectivity relies on an array of device drivers designed to manage the protocols and hardware functions of network interfaces. Device registers. A device register is the interface a device presents to a programmer where each I/O device appears in the physical address space of the machine as a memory address. The operating system reads and writes device registers to control the device. There are 3 types of device registers: status, command, and data. The status register provides information about the current state of the device, e.g. read. The command register issues a command to the device, e.g. writing a value to the register, and the data register is used to transfer data between the computer and the device. Device registers use bits to service 3 purposes: parameters provided by the CPU to the device, status bits provided by the device, and control bits set by the CPU to initiate operations. Figure 6.8 provides an example of the content of each of a device register's bits. A diagram showing sectors and device register bits. It shows bit 1, number of first sector to read, bit 2, operation complete or error occurred, bit 3, start disk read. Figure 6.8 device register bits define the first sector to read, the status of the operation, and the operation itself. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. The behavior of device registers is different from that of ordinary memory locations. For example, the start operation bit may always read as 0, and the bits may change from one status to another, i.e., the operation complete bit may change without being written by the CPU. The OS uses the device register to communicate with an I/O device as follows. The CPU writes device registers to start the operation. The CPU pulls the ready bit in the device register. The device sets the ready bit when the operation is finished. The CPU loads the buffer address into a device register before starting the operation to define where to copy data read from disk. Fast storage media devices move data directly to from physical memory via direct memory access, DMA. Other devices require the intervention of the CPU via programmed I/O or interrupt-initiated I/O. Interrupts allow the CPU to do other work while devices are operating, and the OS figures out which device interrupted. Concepts in practice. Operating systems, printing, and networking. Pretty much anyone needs to print a document these days. It is therefore important to understand how an operating system enables us to print documents so easily. When an application wants to print a document, it hands that task off to the operating system. The operating system sends instructions to the printer's drivers, which then send the correct signals to the printer. Being able to access the network is another critical need in today's business world. It is therefore important to understand how OSs facilitate access to the network and how they control it. When a user uses an application that interacts with the internet, the application sends messages from process to process using the OS's Transport Layer Socket API. These messages are then split into packets within the operating system and eventually passed to a network interface card device, which transmits them to the internet. Figure 6.9 depicts the device register for a keyboard. Note that it has 2 bytes, 16 bits. The data is in the first byte, and the second byte includes all zeros, i.e. from bit 8 to bit 15. When the user starts typing, the ready bit, which is bit number 15, sets to 1. A diagram showing the device register for a keyboard. Figure 6.9 in this device register for a keyboard, the ready bit is set to 1 for when a user starts using the keyboard. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. OS structure. In this section, we learn about the organization and structure of the OS. As you may recall, an OS consists of many core components, but also includes other components such as privileged and non-privileged system programs. In an OS, it is important to have dual mode operations to ensure a high level of security and authority. The dual mode is responsible for separating the user mode from the kernel mode. A program that can run only in the kernel mode is known as a privileged system program. An example of a privileged system program is the bootstrap code, which is the first code that is executed when the OS starts. The OS depends on the bootstrap to be loaded and to work correctly. Figure 6.10 demonstrates the bootstrap use. If the user attempts to make any execution on privileged systems instructions, the execution will not be performed. A diagram shows the bootstrap program. It shows an arrow from main memory, including bootstrap and OS, going to devices. Figure 6.10 to start using any device, the OS will use the bootstrap program. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. A program that can run only in the user mode is called a non-privileged system program. An example of a non-privileged system program is reading the processor status and the system time. In general, this is an instruction that any application or user can execute. Designing a large, complex program is a major software engineering challenge because the program must not only perform well, but it must also be reliable, extensible, and backward compatible. OS design has been an evolutionary trial and error process. Successful OS designs have had a variety of architectures, such as monolithic, layered, cloud infrastructure and exokernels, microkernels, and virtual machine monitors. As the design of an OS, and even its role, are still evolving, it is simply impossible today to pick one correct way to structure an OS. The choice of OS architecture depends on various factors, including the specific requirements, trade-offs, and goals of the OS's intended use. Monolithic OS design. A monolithic design refers to a specific architecture for OSs where the entire OS operates within the kernel space, and all components and functionalities of the operating system are organized within the space. In a monolithic architecture, the entire operating system functions as a single, integrated unit, and all of its components, such as process management, file systems, device drivers, and memory management, reside and operate within the same address space, known as the kernel space. This means that the entire OS operates as a single, large program, and any module or component can directly call the functions of another without any restrictions. While a monolithic design simplifies the communication and interaction between OS components, it has both advantages and disadvantages. One advantage is that it generally provides efficient and fast communication between different parts of the OS because they share the same address space. Another major advantage of the monolithic design is that it uses a familiar architectural style, and the cost of module interactions in terms of procedure calls is low. However, there are many disadvantages. Namely, this structure is hard to understand, modify, or maintain, and does not support fault containment. A failure in any one component can potentially crash the entire system, making it less fault-tolerant compared to more modular architectures. In this case, the alternative is to find an organizational way to simplify the OS design and implementation. Traditional OSs such as Unix, Figure 611, were built using the monolithic architecture. In contrast to monolithic designs, other OS architectures such as microkernel or hybrid designs distribute OS functionalities into separate modules or user space processes, leading to better modularity and potentially improved system stability. A diagram showing how the OS works as one piece in the monolithic architecture. It shows Application 1, Application 2, and Application N with arrows to operating system and an arrow from OS to hardware. Figure 6. 11. The entire OS works as one piece in the monolithic architecture. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. Layered OS design. One alternative way to achieve monolithic OS design is the layered OS architecture, which consists of implementing the OS as a set of layers where each layer exposes an enhanced virtual machine to the layer above, as illustrated in Figure 6. 12. A diagram shows a layered OS architecture. It shows Application 1, Application 2, and Application N with arrows to operating system, with multiple arrows passing through layers of the OS and an arrow to hardware. Figure 6.12. In a layered OS architecture, the OS is divided into layers, and each layer will be responsible for a specific task. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. The first example of a layered approach was Dijkstra's The System, which was designed in 1968. There were 6 layers, and they were organized as follows. Layer 5. A job manager executes users' programs. Layer 4. A device manager handles devices and provides buffering. Layer 3. A console manager implements virtual consoles. Layer 2. A page manager implements virtual memories for each process. Layer 1. A kernel implements a virtual processor for each process. Layer 0. Hardware is the physical components of the computer. Each layer in this setup can be tested and verified independently. Layering also helped with implementation and supported attempts at formal verification of correctness. If you can call only layers below, it is not possible to run into a loop across the various layers. There are, however, many disadvantages to using the layered OS architecture. Namely, it imposes a hierarchical structure, while real systems are more complex because a file system requires virtual memory, VM, services, and the VM likes to use files for its backing store. Layering also imposes a performance penalty, as each layer crossing has overhead associated with static versus dynamic enforcement of invocation restrictions. There is also a disconnect between model and reality, as systems modeled as layers may not really be built that way. Hardware abstraction. The hardware abstraction layer, HAL, is an example of layering in modern OSs, and it allows an OS to interact with a hardware device at a general or abstract level rather than going deep into a detailed hardware level, which improves readability and maintainability. In general, the goal of HAL is to separate hardware-specific routines from the core OS. HAL enables portability of core code across different pieces of hardware. Microkernels. Another alternative OS design to monolithic OS design is a microkernels architecture. Within a microkernel, the functionality and capabilities are added to a minimal core OS as plugins. Microkernel architecture is also called a plugin architecture because functionalities are added as plugins, Figure 6.13. A diagram shows microkernel architecture. It shows Application 1, Application 2, and Application N with arrows to operating system. Within operating system, there are layers of user processes and system processes, labeled user mode. Below these layers is another layer labeled kernel mode with microkernel with arrows to plugin component 1, plugin component 2, and plugin component M. This has an arrow to hardware. Figure 6. 13. In the microkernel architecture, kernel mode is divided into multiple plugins to process the operations. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. The goal of a microkernel architecture is to minimize what goes into the kernel and implement everything else that traditionally goes in an OS in terms of user-level processes. This results in improving reliability due to the isolation between components. Also, there is less code running at full privilege and greater ease of extension and customization. However, performance is generally poor due to user and kernel boundary crossings, which represent a security risk when the kernel code operates on the data. The first microkernel system was Hydra, CMU 1970, followed by Mach CMU, Chorus, French Unix-like OS, and OS X Apple. Windows OS used to use a microkernel, but now uses a hybrid kernel architecture that combines the benefits of monolithic, microkernel, and plug-in OS architectures, Figure 614. A diagram showing Windows OS as plug-in architecture. It has three layers: user mode with Microsoft applications, and kernel mode with microkernel arrows to scheduling, memory management, file system, and hardware. Figure 614 Windows OS as plug-in architecture. In Windows OS, all of the applications are in the user mode, and the OS operations are divided into plugins in kernel mode. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Link to learning. Read this article about how Apple uses kernel architecture in its macOS. Cloud infrastructure and exokernel. Two concepts that each represent critical advancements in the field of computing by offering different methodologies for resource abstraction, allocation, and management are cloud infrastructure and the exokernel. The exokernel architecture simplifies the OS by making its core, kernel, really small and letting apps have more control over the computer's hardware. Unlike usual systems that hide hardware details, an exokernel shows these details to apps, letting them use the hardware more smartly. This way, it cuts down on unnecessary steps and lets each app manage resources its own way, which can make the computer run better and faster. This design is especially good for special computing tasks where apps can really benefit from managing hardware directly, and this can lead to better performance and more efficient use of the computer's parts. There are several limitations associated with exokernels. They lack abstractions for operating system services, which makes it difficult to achieve consistency across applications. They also require an application developer to manage resource allocation and protection and to implement security mechanisms, which raises concerns. The virtualized and scalable hardware resources that are delivered over the internet as a service are called cloud infrastructure. This infrastructure encompasses a range of components including servers, storage devices, network equipment, and virtualization software, all hosted within data centers managed by cloud service providers. Unlike traditional physical infrastructure, cloud infrastructure offers flexibility, scalability, and accessibility, allowing users to access and manage computing resources remotely through the internet. Cloud infrastructure is categorized into three service models. Infrastructure as a service, IaaS, provides virtualized computing resources over the internet, such as AWS EC2, Google Compute Engine, and Microsoft Azure VMs. Platform as a service, PaaS, offers hardware and software tools over the internet, typically targeting developers such as Google App Engine and Microsoft Azure. Software as a service, SaaS, delivers software applications over the internet, accessible from a web browser without installation or running on the user's personal devices such as Google Workspace and Microsoft Office 365. The main disadvantages of cloud infrastructure are potential downtime, security and privacy concerns, vulnerability to attacks, limited control and flexibility, vendor lock-in, cost concerns, latency issues, internet dependency, technical issues, lack of support, bandwidth issues, and varied performance. Technology in everyday life. Remote emailing. Virtual machines have an impact on every industry today as they facilitate the running of numerous business applications. For example, most companies use Google Mail or Microsoft Outlook to supply their employees with email services. These are software as a service, SaaS, cloud infrastructures that operate the email software by making use of virtual machines that run in Google and Microsoft cloud data centers. A major advantage of SaaS email might be portability. Because the application can run on any local machine with an appropriate browser, this enables users to use the app on many different platforms, including mobile phones and tablets. In addition, there is an automatic backup of saved data and no need for complicated installations and configuration. The disadvantages of SaaS might include the lack of security of the data stored in the app with respect to unauthorized access and the inability of users to use the application when the network connection is weak or non-existent. Learning objectives. By the end of this section, you will be able to explain what processes are and how they interact with the operating system. Discuss how operating systems support concurrency. As we mentioned before, the OS divides the tasks it needs to perform into processes. It would be a waste of time for every process to wait until the current process completes. Instead, the OS performs more than one task at the same time, or concurrently. The computing model that improves performance when multiple processors are executing instructions simultaneously is concurrent processing. In this module, we learn about processes and concurrency by digging down into process management and interprocess communication, IPC, threads, scheduling and dispatching, and synchronization. Process. To review, a process is a fundamental concept in an OS that represents an instance of a program in execution. It's an abstraction used by the OS to provide the environment a program needs to run. When we talk about a program, we are typically referring to a set of instructions stored on disk. These instructions are passive and don't do anything by themselves. However, when the program is loaded into the memory of a computer and begins execution, it becomes an active entity known as a process. This transformation is crucial for any computational task, as it moves the program from a static state into an active one where it can perform actions, manipulate data, and interact with other processes. Concepts in practice. Under the cover, most of the applications we use today on our smartphones or laptops use IPC and a client-server architecture. It is therefore important to understand what is under the cover in case these applications suddenly stop working. In an OS, client-server communication refers to the exchange of data and services among multiple machines or processes. One process or machine acts as a client requesting a service or data, and another machine or process acts like a server providing those services or data to the client machine. The communication between server and client uses various OS protocols and mechanisms for message passing, including sockets, remote procedure calls, and interprocess communication. Process management. A process consists of at least an address space, a CPU state, and a set of OS resources. A process's address space is illustrated in Figure 6.15. As you learned earlier in this chapter, the address space contains the instruction code for the corresponding running program and the data needed by the running program. The data can be static data, which does not change within the program, or heap data, which serves a collection of elements and uses a tree or stack data structure. A CPU state consists of the program counter, the stack pointer, SB, and general-purpose registers. The PC is a CPU register located in the processor that has the next instruction address. The stack pointer SB is a register that indicates the location of the last item that was added to the stack. A general-purpose register, GPR, is an extra register that is used for storing operands and pointers. GPRs are where the instructions can read and write the value of their parameters, mostly when the program is interrupted. There are many OS resources such as the CPU, network connections, file storage, I/O, and sound channels. An address space, CPU state, and OS resources are everything you need to run the program or to resume it if it is interrupted at some point. A diagram shows a process's address space. It includes stack dynamic allocated mem, heap dynamic allocated mem, static data segment, and code text segment. Figure 6.15, a process's address space includes the stack pointer SB and the program counter PC. It has static data in the data segment and code in the text segment. Attribution, copyright Rice University, OpenStax, under CC by 40 license. The OS's process namespace particulars depend on the specific OS, but in general, the name of a process is called a process ID, PID, and it has an integer type. A PID namespace is a set of unique numbers that identify processes. The PID namespace is global to the system, and only one process at a time has a particular PID. It is possible to create a container to isolate a process, along with only the files and configurations necessary to run and operate it. This type of isolated process environment allows for greater security, consistency, and portability across different systems. PID namespaces allow containers to provide functionality, such as suspending the set of processes and resuming different set of processes in the memory. The OS maintains a data structure called the Process Control Block, PCB, or Process Descriptor, to keep track of a process state and to store all of the information identified by the PID about a process. As illustrated in Figure 6.16, the PCB contains information that serves as metadata for the process, such as PID, process state, parent process ID, PPID, execution state, PC, SB registers, address space info, and user ID, UID. A diagram shows PCB data structures, process ID, process state pointers to parent-child processes, program counter, stack pointer, registers, address space, user, group IDs, open file list, process priority. Accounting info, process I/O status, exit code value. Figure 6. 16 PCB are data structures that an OS uses to store detailed attributes for each process it is tracking. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Suppose that there's a process that needs input from a user. Because the OS does not use any CPU while waiting for this input, it marks the process in the PCB as suspended. When the user enters the input, the process's status in the PCB changes. The OS keeps the details relating to all of a process's execution state in the PCB when the process is not running. The CPU state, GPC, SB, GPRs, is transferred out of the hardware registers into the PCB when execution is suspended. When a process is running, its state is spread between the PCB and the CPU. Here is an example in Linux that illustrates how to use the PID when creating a child process from a parent main process, which uses the fork command in C, #include unist, include stdio, int main, forking to create a new process. PID equals fork, if PID equals 0. Child process. Print this is the child process with PID%D\n, getPID. Else if PID. Parent process. Print this is the parent process with PID%D\n, getPID. Else. Fork failed. Print fork failed, \n, return 1. Return 0. Interprocess communication. Processes provide isolation to guarantee a high level of protection, but sometimes these processes need to communicate and collaborate. This is made possible via interprocess communication, IPC, which is a mechanism that enables different processes running on an operating system to exchange data among themselves, and thus allows these processes to communicate and collaborate. As Figure 6.17 shows, IPC allows one process, P1, to provide input to another process, P2, while yet another process, P3, is also running. A diagram shows the following. Input process P1, out P1 process P2, out P2, input process P3, out P3. Figure 6.17 in this example of interprocess communication, IPC, the process P1 has an output called out P1 that will be the input that process P2 needs to start working. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. Link to learning. Read this article on interprocess communication to learn more about how the processes running in a computer system can be independent or non-cooperating. Streams, pipes, and sockets. The IPC has a range of mechanisms that enable processes to communicate with each other, such as pipes, shared memory, and sockets. A pipe, sometimes called a named pipe, is a data communication method between two processes that uses a specific name and standard I/O operations, and thus allows for data transfer within a file system. Shared memory allows the processes to communicate with each other without a middleman. A socket is an endpoint for sending and receiving data between different machines in the same network using Internet protocols. What this means is that, for example, in Figure 6.17, where process P1 provides input to process P2, there are many ways for the IPC to deliver this input. It could send command line arguments that are available only to the parent process, i.e., input data is passed to a program when the program is invoked from a shell, or it could communicate via files, e.g. one process writes, the other process reads. Alternatively, the IPC could optimize file communication via the use of pipes with memory buffers, effective when processes are related, or it could utilize environment variables, i.e. variables defined within a shell that can hold a dynamically allocated value, concurrency. Multiple activities and processes happening at the same time. In other words, the OS handling multiple tasks at once is called concurrency. Concurrent processing can be achieved via a multiprogramming environment, a multiprocessing environment, or a distributed processing environment, Figure 6.18. In a multiprogramming environment, multiple tasks are shared by one processor. In a multiprocessing environment, two or more processors that have a shared memory are used. In a distributed processing environment, two or more computers are connected by a communication network, and there is no shared memory between the processors, i.e., each computer has its own memory. Multiprocessing is used to accelerate processing by running tasks in parallel, while distributed computing environments are typically used to implement client-server or peer-to-peer architectures. As noted earlier, and as will be investigated further in this section, threads are another means of achieving concurrency. However, true parallelism can only be achieved by using multiple processors to execute multiple threads simultaneously. A diagram showing concurrent processing. It includes three trees: multiprogramming environment, multiprocessing environment, distributed processing environment, Figure 6. 18 concurrent processing, in which the OS handles multiple tasks at once, can be achieved through three different types of environments. Attribution. Copyright Rice University, OpenStax under CC by 4. 0 license. Link to learning. Read this article on concurrency in operating systems to learn more about the principles and problems associated with the concept of concurrency. Thread. As discussed earlier in this chapter, processes represent running programs, and threads enable programs to perform multiple things at once. A process is an instance of a program that is being executed by an OS. Each process has its own memory space and resources. The OS creates a new process for every executed program and allocates the required resources for the process. For example, it allocates a specific size of memory and CPU time. The process may have one or more threads. Each thread has its own context, but all of the threads within a process share the same resources. Threads are the OS's unit of concurrency and the abstraction of a virtual CPU core. Each thread is a basic unit of execution that executes a set of instructions in a specific order. A thread is a lightweight process that shares OS resources, e.g., memory and I/O, with other threads within the same process. Threads are created by the OS kernel, and each thread has its own register stack. All the threads in a given process are sharing the same memory space. Threads are essentially paths of execution that operate within the confines of a process. For example, consider today's web browsers. Each open tab in a web browser is its own process with its own address space, but within a tab, there might be multiple things going on. A user can scroll around and interact with a web page while a video is playing in the background. In this case, one thread could be used to manage the user interactions, while another thread is used to manage video playback on the web page. In the early versions of the operating system used on IBM and DEC mainframe computers, concurrency was achieved via time sharing. In other words, a single task was performed using a single process with a single thread. This kind of process allowed only one user at a time to process or run a job. This old way of processing required more resources such as memory and processors to finish a single task. By the late 1970s, the more prominent approach became multitasking, which makes it possible for the OS to run multiple processes at the same time using time slicing. A time slice is a short time frame that gets assigned to a process for CPU execution. It corresponds to the time frame during which a process is allotted to run in preemptive multitasking CPUs. In that case, a scheduler runs each process every single time slice. The preemptive multitasking approach was not sufficient to improve the OS performance, so 20 years later, OSs still support multitasking using multiple threads. Figure 6.19 illustrates single and multi-threaded processes. A pair of diagrams shows a single-threaded process and a multi-threaded process. Figure 6.19 in the single-threaded process, a single thread will use its own code, data, and files along with its own registers and stack. In the multi-threaded process, a multi-thread will have a set of registers and stacks. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. When a program is run, it operates as a process in the OS. This process can execute multiple threads simultaneously, allowing for parallel execution of tasks within the same application environment. The threads are managed and run as follows. Thread creation. Threads are created by the process using specific system calls to the operating system, such as pthread create in Unix Linux or create thread in Windows. When created, each thread starts its execution at a designated start point in the program code. This is often a function passed to the thread creation call, execution, and scheduling. Once created, threads are scheduled by the operating system scheduler, which allocates CPU time to them. The scheduling can be preemptive, where the OS decides when to switch between threads, or cooperative, where threads voluntarily yield control to allow other threads to run. Sharing and isolation. Threads share the same process resources, such as memory and file handles. making interprocess communication and data sharing more efficient than between separate processes. However, they run in their own thread of execution, meaning each has its own stack, program counter, and set of registers to keep track of its execution state, synchronization. To safely manage the access to shared resources and ensure data consistency, threads often use synchronization mechanisms like mutexes, semaphores, and condition variables. These tools help prevent race conditions, where the outcome of operations depends on the sequence or timing of other uncontrollable events. Completion. A thread completes its execution when it exits its start function, either by returning normally or by being explicitly terminated by itself or another thread. Upon completion, any resources specifically allocated to the thread are cleaned up by the operating system. Scheduling, dispatching. Scheduling tasks and determining which resources should be used when are central responsibilities of the OS. They are also the means by which the OS achieves concurrent processing. OSs may switch the CPU from process to process hundreds of thousands of times per second. On today's hardware, this takes a few microseconds. Choosing which process to run next is called scheduling. The activity of handling the removal of the running process from the CPU and the selection of another process based on a particular strategy is called scheduling. In OSs, a process can be in one of several states. These states are part of the process lifecycle, and understanding them is essential for grasping how the OS manages processes. The specific names and number of states can vary between OSs, but the fundamental concepts remain the same, or at least quite similar. Each process has an execution state, which indicates what it is currently doing and can be as follows: ready, waiting to be assigned a core; running, executing on a core; blocked, also known as waiting, waiting for an event, so not eligible to be given a core. Figure 620 represents a process's lifecycle within an OS. It starts with the creation of a process, which brings a new process into existence and places it in the ready state. In this state, the process is loaded into memory and is prepared to run, but is waiting for the CPU to become available. When the scheduler dispatches the process, it transitions to the running state, where it is actively executing its instructions. If the process is interrupted, it reverts to the ready state, waiting once again for a chance to run. Certain events, such as I/O requests or page faults, can cause the running process to experience a trap or exception. When this happens, the process enters the blocked state because it can't proceed until the event it's waiting for, such as the completion of an I/O operation, occurs. Once the awaited event is finished, the process can leave the blocked state and re-enter the ready state, once again waiting for CPU time. When a process completes its execution or is terminated, it reaches the terminate state. However, termination doesn't necessarily mean the process is immediately removed from the system. It may enter a zombie state. In this state, the process has finished its job, but still occupies an entry in the process table, effectively being in a state of limbo until its parent process acknowledges its completion. This acknowledgement allows the OS to fully clean up any remaining information, officially ending the process's life cycle. A diagram shows the life cycle of a process within an OS. It includes running, ready, blocked, figure 620. The life cycle of a process within an OS starts with the creation of the process and ends with an acknowledgement of completion. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. As noted earlier, each process is represented by a unique identifier called a process identifier, PID. An OS encapsulates the process in a data structure type called a process control block, PCB, that contains information about the process, such as current status, which could be running status, ready status, or blocked status. A PCB defines the register status, the process ID, the execution time, the memory space, as well as other information. The OS kernel scheduling function is responsible for maintaining the content of PCB and scheduling processes for the CPU to execute based on assigned priorities. Another policy decision the OS makes is to decide whether to give out non-CPU resources such as memory and I/O, as they are data structures. PCBs are located in OS memory. When a process is created, the OS allocates a PCB for it. After initializing the PCB, the OS then does other things not related to the PCB, such as allocating the PCB to the correct queue. As a process executes, the OS moves the process's PCB from queue to queue. When a process is terminated, the PCB may be retained for a while. Eventually, the OS deallocates the PCB. The act of switching the CPU from one process to another is called a context switch. Context switching is a procedure that a computer's CPU follows to change from one task to another while ensuring that the tasks do not conflict. In Figure 6.21, the process P0 is in the running state, and the process P1 is in the ready state. When an interruption occurs, the process P0 must be switched from the running to the ready state, and the process P1 must be switched from the ready to the running state. To accomplish this, the OS performs these steps. It saves the context of the process P0 in PCB0, switches P0 from the ready state, selects P1 to be executed, and finally, updates PCB1 of process P1. A diagram shows an example of context switching with steps involved when a CPU switches from executing process P0 to running process P1 and then back to P0. Figure 6.21. This example of context switching shows the steps involved when a CPU switches from executing process P0 to running process P1 and then back to P0. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Transactions and scheduling. As you've learned, scheduling is the act of determining which process is in the ready state and should be moved to the running state when more resources are requested than can be granted immediately, and in which order such requests should be serviced. Examples are processor scheduling, i.e., one processor, many threads, and memory scheduling in virtual memory systems. A good scheduling algorithm minimizes response time, efficiently utilizes resources, that is, it ensures full utilization by keeping cores and disks busy, with minimal context switches, and implements fairness by distributing CPU cycles equitably. Ideally, scheduling algorithms should not affect the results produced by the system. Optimal scheduling schemes would require the ability to predict the future, making adaptive algorithms the preferred choice. Examples of simple scheduling algorithms include first come, first served FCFS scheduling, also called first in, first out FIFO. In this algorithm, the first job that comes to the processor is executed first. For example, suppose we have two processes, process P1 with execution time 3 and process P2 with execution time 2. The arrival time for both process P1 and process P2 is T0. The system will start with process P1 at T0 and finish at T3, and process P2 will start at time T3 to time T5, as shown in Figure 6.22. The wait time for process P1 is 0, and the wait time for process P2 is 3. A diagram shows process P1, execution time equals 3, process P2, execution time equals 2. Below it shows time T0, time T3, and time T5. Figure 6.22. Two processes, P1 and P2, are being processed using the FCFS algorithm. Attribution. Copyright Rice University, OpenStax, under CC by 40 license, round-robin scheduling, RR. This algorithm, which is widely used in time-sharing systems, is designed to ensure fairness among processes by giving each process an equal share of the CPU. Its operation is relatively straightforward, but effective in environments where a large number of processes need to be handled efficiently. The core idea of RR scheduling is to assign a fixed time slice, often referred to as a quantum, to each process in the ready queue. The CPU scheduler cycles through the queue, allocating the CPU to each process for a duration equal to 1 quantum. For the previous example, let us set the quantum to 2. Then the processor will execute part of process P1 and move to process P2, then go back to process P1, Figure 6.23. A diagram shows process P1, execution time equals 3, processing time equals 2. Process P2, execution time equals 2, processing time equals 2. Process P3, execution time equals 3, processing time equals 1. Below it shows time T0, time T2, time T4, and time T5. Figure 6.23. Two processes, P1 and P2, are being processed using the RR algorithm. Attribution. Copyright Rice University, OpenStax, under CC by 40 license, shortest time to completion first, STCF, also called shortest job first, SJF. This algorithm takes the best approach to minimize the waiting time, but it requires that the processor knows the processing time in advance. In the previous example, the processor will run process P2 before process P1 because the execution time is less. Shortest remaining processing time, SRPT. In SRPT, the processor is reallocated to a newer ready job with a shorter remaining completion time whenever such a job arrives. Synchronization in concurrent programming is crucial for ensuring that multiple threads or processes can work together without interfering with each other's operations on shared resources. Through mechanisms like locks, condition variables, and semaphores, developers can design systems that are both efficient and safe, avoiding issues such as data races and deadlocks. One way of coordinating multiple concurrent activities that are using shared state is synchronization, which groups operations together automatically to ensure cooperation between threads. To ensure that only one thread does a particular task at a time, we can use a program called mutual exclusion that prevents simultaneous access to a shared resource. A critical section is a piece of code that only one thread can execute at once. Also, only one thread at a time will get into this section of code. A critical section is the result of mutual exclusion. Critical sections and mutual exclusion are in fact two ways of describing the same thing. Critical sections are sequences of instructions that may get incorrect results if executed simultaneously. Mutual exclusion is required to ensure that a process cannot enter its critical section while another concurrent process is currently present in its critical section. Figure 6.24 illustrates a representation of two processes, process P1 and process P2. At time 1, process P1 entered the critical section by printing on a shared printer. Process P1 will finish printing at time 2. While process P1 is printing, process P2 is attempting to print, but the OS will block process P2 from printing until process P1 reaches time 2. A diagram shows process P1 using the printer starting from time 1 and will finish printing at time 2. Process P2 is trying to print while process P1 is printing. The OS will use mutual exclusion to prevent process P2 from starting until process P1 has ended. Figure 6.24 process P1 is using the printer starting from time 1 and will finish printing at time 2. Process P2 is trying to print while process P1 is printing. The OS will use mutual exclusion to prevent process P2 from starting until process P1 has ended. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. A lock is a synchronization mechanism that is used to enforce mutual exclusion. A thread must acquire a lock before entering a critical section. If the lock is already held by another thread, the attempting thread will block until the lock becomes available. Another synchronization mechanism, called a condition variable, is used in conjunction with locks to allow threads to wait for certain conditions to become true. While a lock facilitates exclusive access to resources, a condition variable helps threads wait for specific states of the world. A classic example of a synchronization challenge is the producers-consumers problem, where producers generate data and place it into a buffer, and consumers remove data from the buffer for processing. In a producer-consumer scenario, a consumer might wait on a condition variable if the buffer is empty, and a producer might signal this variable once it adds an item to the buffer. The key concerns associated with this scenario include ensuring that producers don't add data to a full buffer and that consumers don't try to remove data from an empty buffer. Synchronization tools like locks and condition variables are used to solve these issues. A deadlock occurs when a set of threads are blocked forever, waiting for each other to release resources. This can happen, for example, if thread A holds lock 1 and waits to acquire lock 2, while thread B holds lock 2 and waits to acquire lock 1. Avoiding deadlocks requires careful design, such as acquiring locks in a consistent order or using timeout mechanisms. Some other tools used in synchronization are semaphores, similar to locks, but allow multiple threads to access a finite number of resources barriers, enable multiple threads to wait until all have reached a certain point in their execution before any are allowed to proceed read-write locks. Allow multiple readers to access a resource concurrently, but require exclusive access for writers' mailboxes, dedicated channels that connect two processes directly, allowing data to be exchanged between them. Mailboxes behave like queues but use semaphores for controlled automatic access and operate in first-in, first-out FIFO order only. Technology in everyday life, multitasking the ability to run multiple programs at once on computers today, has a huge productivity impact in all industries. In concurrent programming, managing shared resources among multiple threads or processes is crucial for maintaining data integrity and preventing race conditions. One common scenario is the producer-consumer problem, where one or more threads, producers, generate data and others, consumers, consume it. To avoid conflicts, synchronization mechanisms like locks and condition variables are employed. Locks help ensure that only one thread accesses a critical section of code at a time. In the context of the producer-consumer problem, locks can be utilized to safeguard shared data structures, preventing simultaneous access by multiple threads and ensuring data consistency. Condition variables are another synchronization tool that allows threads to coordinate their activities. In the context of producers and consumers, a condition variable could signal when data is available for consumption or when space is available for production. Threads can use these signals to efficiently wait for or notify others about the state of shared resources. The combination of locks and condition variables provides a powerful means to synchronize complex interactions between producers and consumers, ensuring orderly access to shared resources. Despite the benefits of synchronization mechanisms, the improper use of locks can lead to issues like deadlocks, where two or more threads or processes are stuck in a circular wait, unable to proceed because each is waiting for the other to release a resource. This situation can bring a system to a standstill, and careful design and coding practices are necessary to prevent or detect and recover from deadlocks. To handle deadlocks, techniques such as deadlock detection algorithms and prevention strategies are employed, contributing to the robustness of concurrent systems. Allocation, the method that defines how data is stored in the memory, by providing a set of requests for resources and identifying which processes should be given which resources to make the most efficient use of the resources, is called allocation. Like scheduling, allocation is another kind of decision-making that an OS performs about how to use resources to support concurrency. There are three main forms of allocation: contiguous allocation, linked allocation, and indexed allocation. In contiguous allocation, each file is assigned to a contiguous, i.e., neighboring set of blocks in the memory. For example, if a file requires 3 blocks and is given a starting location x, the file will be allocated in x, x plus 1, x plus 2. The directory entry with contiguous allocation contains the starting block address and the length of the file. In linked allocation, each file is a linked list of memory blocks. Using the same example, the first block will be allocated in location x, and it will include the address of the second block. The directory entry with linked allocation contains a pointer to the starting block and a pointer to the last block. In indexed allocation, each file has an index block containing the pointers to all blocks for that file. Learning objectives. By the end of this section, you will be able to discuss key concepts related to memory, evaluate dynamic storage management solutions, discuss the differences between virtual and physical memory. As you have learned, memory plays a huge role in OSs. Here we discuss the memory multiplexing, linkers and dynamic linking, dynamic storage management, virtual memory, and demand paging. Memory. Different processes and threads share the same hardware. It is therefore necessary to multiplex the CPU, i.e., temporal execution, memory spatial access, and disks and devices. As discussed earlier, the complete working state of processes and/or kernels is defined by its data. Memory, registers, and disk. For the sake of safety, security, and reliability, processes should be barred from having access to each other's memory. Dividing the capacity of the communication channel into multiple logical channels is considered memory multiplexing. There are several concepts that are critical to memory multiplexing, namely isolation, sharing, virtualization, and utilization. As you learned earlier in this chapter, isolation is important because it ensures that the multiple programs that are running concurrently on the same CPU and memory operate independently without interfering with each other's execution or data. In memory multiplexing, isolation is achieved through a set of technologies that prevent distinct process states from colliding in physical memory due to unintended overlap, i.e., overlap control. These technologies aim to, for example, prevent process P1 from spying on process P2, or if process P1 has a bug, they ensure that this bug does not impact process P2. There are many isolation mechanisms, including user kernel mode flag is a register that represents the CPU mode as user mode or kernel mode. As we have learned, the CPU boots in kernel mode, then it marks the flag as kernel mode. When the user starts any application, the CPU marks the flag as user mode. Address space boundaries protect the kernel and address space programs from each other. System call interface is the programming interface for application users to process a system call. As shown in Figure 625, a system call is executed by the user mode to request the kernel mode to perform a specific action, e.g. syscall function. A diagram shows a system call interface using an isolation mechanism to address a system call. Figure 6.25, the system call interface uses an isolation mechanism to address a system call, which is a request that arises from the user mode and requires the kernel mode to perform an action. The system call interface prevents these processes from overlapping or colliding. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Time slicing provides a time frame for each process to run in a preemptive multitasking CPU such that each process runs every single time slice. If the process finishes the job before the time slice, it releases the CPU and does not need to be swapped out. If the time slice ends and the process did not finish the job, the CPU shifts it out to the end of the process's queue. For example, assume we have three processes P1 with execution time 3 ms, P2 with execution time 4 ms, and P3 with execution time 2 ms, and a time slice of 2 ms. Figure 6. 26 illustrates how the CPU manages the processing using time slice and indicates in which time slice each process completes execution. A diagram shows three processes P1, P2, and P3 working as scheduled based on the time slice. Figure 6.26 The three processes P1, P2, and P3 blue will work as scheduled based on the time slice. The processes are scheduled in the queue and executed, so they come out of the queue arrow. Empty spaces in the queue are shown in pink. Attribution, copyright Rice University, OpenStax, under CC by 40 license. When multiple processes can use the same piece of data concurrently, it is called sharing. The option for overlapping processes should be available when desired for efficiency and communication reasons. Memory sharing improves the performance of the system because the data is not copied from one address space to another, so memory allocation is done only once. With respect to memory, virtualization is a technique that gives an application the impression that it has its own logical memory and that it is independent from the available physical memory. Thus, in virtualization, there is a need to create the illusion that there are more resources than those that actually exist in the underlying physical system. There are two approaches of memory virtualization: full virtualization and guest modification. When multiple operating systems run concurrently on a single physical machine, fully isolated from each other, by emulating hardware resources through a hypervisor, it is called full virtualization. For full virtualizations, all OSs expect contiguous physical memory that starts from physical address 0. In the context of virtualization, guest modification refers to altering the guest operating system or its configuration to improve compatibility, performance, or integration with the virtualization environment or hypervisor. Guest modification modifies the OS to avoid using instructions that virtualize inefficiently. An optimal use of limited resources is warranted to guarantee a high level of utilization. Processes use different amounts of memory, and their memory needs change over time. Whenever a new process cannot fit into contiguous space in physical memory, it results in fragmentation, specifically external fragmentation. When the memory blocks cannot be allocated to the processes due to their small size and the blocks remain unused, this problem is called fragmentation. There are two types of fragmentation: internal fragmentation and external fragmentation. When the process is allocated a block and its size exceeds the process size, it leaves part of the memory allocated unused and results in internal fragmentation. In the external fragmentation, the total space that is needed for the process is available, but we can't use it because the space is not contiguous. Linkers and dynamic linking. Linkers are software tools that an OS uses to combine object files into an executable file. A linker performs name resolution, matching the name of a variable or function in an application to a virtual memory address it will have when loaded and run. A linker combines many separate pieces of a program, reorganizes storage allocation so that all the pieces can fit together, and touches up addresses so that the program can run under the new memory organization. After a linker completes the task of combining multiple object files generated by a compiler into a single executable file, the executable file can be loaded and executed by the OS. Figure 6.27. A diagram shows a linker process with arrows going from object and library to linker, and arrows from linker going to exe, library, and DLL. Figure 6.27. A linker process includes object files and libraries. Attribution, copyright Rice University, OpenStax, under CC by 40 license. The mechanism that allows a program to associate external code symbols to addresses at runtime is dynamic linking. The allocation process starts when the process is running by dividing the memory into smaller parts called segments. For example, Linux's memory layout is divided such that the code starts at location 0, the data starts immediately above the code, and the stack starts at the highest address, as illustrated in Figure 6.28. When a process is started, the OS will load the file to the memory, with the added option of sharing the memory with others. The OS facilitates the memory size at runtime by adding more assigned memory when needed. A diagram shows a Linux memory layout. The code starts at location 0, the data starts immediately above the code and grows upward, and the stack starts at the highest address and grows downward. Figure 6.28. In Linux's memory layout, the code starts at location 0, the data starts immediately above the code and grows upward, and the stack starts at the highest address and grows downward. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. In dynamic linking, the code is located and loaded when the program is first run. Since the late 1980s, most systems started supporting shared libraries and dynamic linking by only keeping a single copy of common library packages in memory that is shared by all processes. This means that the system does not know where the library is loaded until runtime and must resolve references dynamically when the program runs. Dynamic storage management. There are two basic operations used in dynamic storage management to manage a memory or storage to satisfy various needs. Allocate a block with a given number of bytes or free a previously allocated block. There are two general approaches to applying these dynamic storage allocation operations. 1. Stack allocation, which is hierarchical and restricted, but simple and efficient. And 2. Heap allocation, which is more general but more difficult to implement and less efficient. The linear data structure that follows a LIFO order, last in, first out, as in the stack data figure configuration in Figure 6.29, is called stack allocation. In the stack approach, the memory is freed in opposite order from allocation. For example, if procedure X calls Y, then Y will certainly return before returning from X. Stacks take advantage of this programming practice to store the state of the current procedure call. When memory allocation and freeing are partially predictable, then a stack approach can be used. A diagram shows stack data structure. From right to left it shows push stack, pop. Figure 6.29. This stack data structure representation shows a last in, first out approach. Attribution. Copyright Rice University, OpenStax under CC by 4.0 license. Allocating the data in a tree-based data structure called a heap is heap allocation. A heap is represented by a complete binary tree. As shown in Figure 6.30, a heap data structure can be of two types: max heap and min heap. Max heap presets the root node with the greatest value, and the same for the subtrees. It is the opposite for the min heap, where the root will have the minimum value, and the same for the subtrees. A diagram shows heap allocation structure, showing the structure of both max heap and min heap. Figure 6.30. Heap allocation uses a data structure called a heap to manage memory and storage. There are two types of heap structures or trees, one for the max heap and one for the min heap. Attribution. Copyright Rice University, OpenStax under CC by 4.0 license. Memory managers, such as the ones used in C and C++, do not actually store available memory in a heap data structure. Instead, they manipulate a doubly linked list of blocks, which they confusingly refer to as a heap, and attempt to optimize memory using a best-fit method. Memory managers use the heap approach when the allocation and release of memory are not predictable, i.e., when it is not clear how much memory is needed until we run the program. Typically, the heap stores data structures that can change in size over time based on how many elements are added or removed from the data structure. The corresponding heap memory consists of allocated areas and free areas, or holes. Virtual memory. The key component of the operating system that ensures process isolation by guaranteeing that each process gets its own view of the memory is virtual memory. A running program, process, has a seemingly infinite view of memory and can access any region without worrying about other programs that might also be running on the computer. The OS seamlessly translates each process memory request into a separate region of the physical hardware memory through address translation. When the system needs to find a physical address in the memory that matches the virtual address, address translation occurs. The running process only deals with virtual addresses and never sees the physical address. Virtual memory is mapped to physical memory in units called pages. There is a time cost associated with performing virtual to physical memory address translation, however, and this can add up given that most programs need access to the memory to store data. To speed up address translation, the CPU has dedicated hardware for caching, storing, recent address translations called a translation look-aside buffer, TLB. A TLB is a memory cache that stores the virtual memory recent transaction to physical memory. TLBs help the CPU avoid making multiple round trips to main memory just to resolve a single virtual memory access by only requiring one round trip, Figure 6. 31. A TLB contains page table entries that have been most recently used. Given a virtual address, the processor examines the TLB table. If a page table entry is present, it's a hit. This means the frame number is retrieved and the real address is formed. If a page table entry is not found in the TLB, then it's a miss. In this case, the page number is used as an index while processing the page table. TLB checks if the page is already in the memory. If it's not, then a page fault is issued, and the TLB is updated to include the new page entry. A diagram shows translation look-aside buffers, TLBs, speeding up address translation by using an approach that involves detecting hits and misses. Figure 631 translation look-aside buffers, TLBs, speed up address translation by using an approach that involves detecting hits, which means a page table entry is present in the TLB, and misses, a page table entry is not found in the TLB. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Link to learning. What is the fundamental concept that makes it possible to implement virtual memory? Check out an explanation of how to implement virtual memory to investigate this question. Demand paging. The storage mechanism that uses a page form in retrieving a process from secondary or virtual memory to main memory is called paging. Virtual memory presented a seemingly infinite amount of memory to the running process, but what happens when the operating system runs out of free physical memory? Modern operating systems also have a backup when DRAM runs out, which means virtual memory can be mapped to disk to meet demand. The storage mechanism in which pages should only allocate in the memory if it is required from the execution process is called demand paging. Figure 6.32 shows a CPU that is demanding pages from the virtual memory to the main memory, i.e. swap in, and releasing pages from the main memory to the virtual memory, i.e. swap out. The working set size WSS refers to the total amount of memory a process requires during a specific period of activity, measured as the set of pages or data blocks the process accesses. WSS is measured by tracking the unique pages a process references over a fixed interval of time. This provides an estimate of the process's active memory footprint and helps in memory management decisions like paging and swapping to optimize performance and resource allocation. A diagram shows demand paging, where a CPU retrieves pages from the virtual memory to the main memory and releases pages from the main memory to the virtual memory. Figure 6.32 in demand paging, a CPU retrieves pages from the virtual memory to the main memory and releases pages from the main memory to the virtual memory. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. When the CPU demands a page, and this page is not present in the main memory, we call this situation a page fault. A page fault occurs when a process references a page that is in the backing store. To handle a page fault, the CPU transfers control from the program to the OS to demand the requested page to the main memory. OS finds a free page frame in memory, loads the page from the backing store to the main memory, and resumes execution of the thread. The CPU has special hardware to assist in resuming execution after a page fault. Given that access to the disk is much slower than DRAM, operating systems are often designed to predictively swap in-use pages into DRAM and out-of-use pages to disk. The process of bringing pages into memory, i.e. demand paging, is called page fetching. Most modern OSs use page fetching by starting the process with no pages loaded and do not load a page into memory until it is referenced. If a requested page is stored on the disk, prefetching, which is the act of trying to predict when pages will be needed and loading them ahead of time to avoid page faults, is performed. If all memory is in use, it is necessary to throw out one page each time there is a page fault. This process is called page replacement. In page replacement, one page in the full DRAM is swapped to disk while the requested page is brought into DRAM. However, if too many processes need access to a lot of memory back and forth between DRAM and disk, this causes problems. For example, each page fault causes one of the active pages to be moved to disk, so another page fault soon occurs, and this leads to thrashing. Thrashing is when a computer's operating system becomes overwhelmed by the number of processes requesting memory. This situation leads to a cycle where the system spends more time moving data between the physical memory and disk storage, paging or swapping, than executing actual processes. It's like a busy restaurant where the staff spends more time rearranging tables than serving food. The main cause of thrashing is often that too many programs are running at the same time. These activities exceed the available memory, causing the system to constantly try to make space for new requests by moving data to and from the disk. Strategies to prevent thrashing include limiting the number of simultaneously running programs to avoid memory overcommitment, optimizing how memory is allocated to processes, and possibly increasing the system's physical memory. By managing memory more efficiently and ensuring that the system is not overloaded with too many tasks, the system can not only avoid a slowdown, but significantly improve its performance. In extreme cases of thrashing, the OS can spend all its time fetching and replacing pages and will not get much work done. This is one reason why our devices can slow to a halt when they run out of memory and each thread must wait on requested pages. Concepts in practice. Impatience with computers. We've all been there at our laptops putting the final touches on a slide presentation, while checking email, while uploading a photo to our social media feed, while listening to a new playlist our friend just shared with us, while watching a video, while inputting data into a spreadsheet and everything freezes. The screen, the keyboard, the trackpad. Not only does nothing do what we ask it to do, it all just goes still. Or worse, the little pinwheel starts spinning and never stops. Now, having read about memory, dynamic storage management, resource allocation, and thrashing, think about what's happening inside your CPU. If you're using a computer that runs Windows, check out this resource to see how you could help your operating system operate better. Learning objectives. By the end of this section, you will be able to explain features of various file systems, discuss file system structures and layers. In this module, we learn about files, file management, disk devices, file system interface, and distributed file systems. Files, file systems, directories, and file management. A file is a collection of related information that is stored on a storage instrument, such as a disk or secondary virtual storage. It is the smallest storage unit from the user's perspective. The file name includes two parts, name and extension, e.g., filename, txt. Each extension is for a specific purpose such as exe in Windows OS to run a program and txt for text files. A file system is responsible for defining file names, storing files on a storage device, and retrieving files from a storage device. When designing a file system for managing many files, some issues to consider are as follows. Most files are small, so per file overheads must be low. Most of the disk space is in large files. Many of the I/O operations are for large files, so performance must be good for large files. Files may grow unpredictably over time. Users want to use text names to refer to files. Special disk structures called directories are used to map names to support hierarchical directory structures. A directory is a set of files that is managed by the OS, and it also contains all the required information about the files, such as attributes, location, and ownership. The Unix-Linux approach is as follows. Directories are stored on disk just like regular files except with extra information to indicate that it is a directory. Each directory contains name, address, pairs. The file referred to by the address may be another directory, hence, we can have nested and hierarchical directory structures. The problems facing modern file systems include disk management, naming, and protection. File systems are often trying to improve access to files by minimizing seeks, sharing space between users, and making efficient use of disk space. A system's ability to reduce faults and ensure that the information in the system survives OS crashes and hardware failures is called its reliability. In addition to improving reliability, a file system should guarantee a high level of protection by maintaining isolation between users and controlling the sharing of resources. Disk devices. While file systems are a layer of abstraction that provides structured storage and defines logical objects such as files and directories, disk devices are considered raw storage. Data that can be directly accessed by the CPU with minimum or no delay and does not survive a power failure is held in primary storage. Persistent memory that survives power failures most of the time, such as spinning disks, SSDs, and USB drives, is considered secondary storage. Routines that interact with disks are typically at a very low level in the OS and are used by many components such as file systems and virtual machines. These secondary storage devices may handle the scheduling of disk operations, error handling, and often the management of space on disks. A trend is for disks to do more of this themselves. File system architectures. Operating systems use various methods to locate files by their names, and the methodology often depends on their underlying file system architecture. To illustrate these concepts, here are some examples from Unix-like systems and Windows. Unix Linux, inodes. In Unix-like systems, the file system uses a structure called an inode to represent files and directories. An inode contains metadata about a file or directory, but not its name. The name-to-inode mapping is stored in directories, which are special files that list names of files and their corresponding inodes. When searching for a file by name, the OS starts at the root directory and follows the path specified in the file name. Each part of the path is looked up in the current directory's list of names and their associated inodes. The OS reads the directory file, finds the name, and retrieves the inode number, which then leads to the inode itself. The inode provides the location of the data blocks, allowing the OS to access the file's data. This process may involve multiple steps if the file is in a nested directory structure. Windows, File Allocation Table, and NTFS. In File Allocation Table, FAT format, files are located using a table that maps file names to the cluster's blocks on the disk where their data is stored. The FAT is essentially a list, with each entry containing the location of the next part of the file. This creates a chain that the OS follows to read the entire file. In New Technology File System, NTFS, files are located using a master file table, MFT, and each file and directory on an NTFS volume has an entry in the MFT containing data, including the file name, size, timestamps, permissions, and the locations of the file's data on disk. When searching for a file, the OS consults the MFT to find the entry corresponding to the file name, which then provides the information necessary to access the file's data. As you may recall, files represent values stored on disk and directories represent file metadata. File systems define operations on objects such as create, read, and write, and they may also provide higher-level services such as accounting and quotas, incremental backup indexing or search, file versioning, and encryption. A quota is the amount of space to store files based on the available memory space. Quotas are used to protect the system from unnecessary load and help in organizing the data in the storage. An incremental backup is a backup image containing the pages that have been updated from the time of the previous backup. The method that converts the data into secret code that hides the data's true meaning is called encryption. The system that allows a file to exist in several versions at the same time, which gives the user complete control over file creation as in the file versioning example, is called file versioning. Figure 633. A diagram shows file versioning. It reads initial version, doc version 1, doc version 2, doc version 3, doc version 4. Figure 633. In file versioning, the OS saves all copies of a file, in this case, a doc or document file. Attribution, copyright Rice University, OpenStax, under CC by 40 license. File systems are concerned with lower-level characteristics, such as performance and failure resilience. Both performance and failure resilience may be strongly affected by hardware characteristics. File system interface. In general, the file system interface defines standard operations such as file or directory, creation and deletion, manipulation of files and directories, copy and lock. Remember, the various file attributes are name, type, size, and protection. The file system uses these attributes to provide system calls for the following operations. Create. Find a space for the file in the disk and enter the new file information in the directory. Write. Search the directory for a specific file and start writing from where the writing pointer is pointing to. Read. Specify the name of the file and start reading from where the reading pointer is pointing to. Seek. Search for the specific byte position in the file. Delete. Search for the file in the directory and erase the file from the directory. Truncate. Reset the file length to 0 and release the allocated space for the file. Append. Add new information to the end of the file. Copy. Create a new file and read the data from an old file, then write it to the new one. If multiple processes are trying to open a file at the same time, then there is a role for file management that should be applied, namely, lock, linked to learning. As people and businesses use various types of computers today, the ability to interchange files between various file systems is critical. In fact, insurance companies often ask their clients to sign insurance contracts over the internet and rely on their digital signature in online documents. Teachers use Google Classroom to enable their students to collaborate on assignments or class presentations. Read this overview of common file systems to see how file systems enable us to seamlessly share documents and files. Inodes. As mentioned earlier, inodes are OS data structures used to represent information about files and folders stored on disk along with file data and kept in memory when the file is open. An inode contains information including file size, sectors occupied by file, access times, e.g. last read and last write, and access information, e.g. owner id and group id. In Linux, whenever the system creates a new file, it gives it an inode unique number called inumber. Internally, the OS uses the inumber as an identifier for the file, in effect as its name. When a file is open, its inode is kept in main memory. When the file is closed, the inode is stored back to disk. If you are using Linux, you can check the total number of inodes on disk using the df command and I option, as shown in Figure 6. 34. The following is shown: df i/dev/sda. Output: filesystem dev/sda. Inodes 1,624,000. I used 128,000. I free 1,496,000. I use %9%. Figure 6. 34. In the Linux OS, the total number of inodes on the directory dev/sda can be viewed using the command df and the option I attribution. Copyright Rice University, OpenStax, under CC by 40 license. File systems are responsible for managing parts of the disk that are used, inodes, and parts of the disk that are not used, free blocks. Each file system has different strategies and approaches for managing this information, with different trade-offs. Additional features of file systems include file system, level encryption, compression, and data integrity assurances. Distributed file systems. A distributed file system, DFS, is a file system that is distributed on multiple file servers or multiple locations that support network-wide sharing of files and devices. The presentation of a DFS is similar to the traditional view, i.e., client is using a file system. The main idea of a DFS is that it uses a namespace, which means all clients see a single namespace where files and directories are shared across the network. In a DFS, clients can read and write files on a remote machine as if they were accessing their local disks. A DFS provides an abstraction over physical disks that is akin to the abstraction virtual memory provides over physical memory, Figure 6. 35. A diagram shows a distributed file system architecture. It includes end-user DFS server disk/local storage cloud, Figure 6. 35. In a distributed file system architecture, the DFS server works like a middleman between the end user and the data, which can be in any storage format. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. DFS technologies like Google's GFS, Google File System, Apache Hadoop's HDFS, Hadoop Distributed File System, and Apache Spark's RDDs, resilient distributed datasets, have revolutionized the way we handle and process large volumes of data. These systems are designed to accommodate high-throughput computing, HTC, complementing the capabilities of high-performance computing, HPC, by focusing on the efficient processing of vast datasets across clusters of computers. Google File System, GFS, is a prime example of a DFS that is highly optimized for large-scale data processing. It is designed to provide high fault tolerance while running on low-cost commodity hardware. Hadoop Distributed File System, HDFS, follows a similar principle, but is open source and commonly associated with the Hadoop ecosystem. It's designed to store very large files across machines in a large cluster and to stream those files at high bandwidth to user applications. By breaking down files into blocks and distributing them across a network of computers, HDFS can process data in parallel, significantly speeding up computations and data analysis tasks. Resilient Distributed Datasets, RDDs, in Apache Spark are a further step in distributed computing, offering an abstraction that represents read-only collection of objects partitioned across a set of machines that can be rebuilt if a partition is lost. Spark's use of RDDs allows it to process data in memory, which is much faster than the disk-based processing used by Hadoop, making Spark an excellent choice for applications requiring quick iterations over large datasets. To facilitate the communication necessary in these distributed environments, protocols such as Remote Procedure Call, RPC, and Distributed Hash Tables, DHTs, are employed. RPC is a protocol that a program can use to request a service from another program, located in another computer in another network without having to understand the network's details. DHTs are a class of decentralized distributed systems that provide a lookup service similar to a hash table. Keys are mapped to nodes, and a node can retrieve the content associated with a given key. Beyond these, the concept of n-tier distributed file systems, such as the Network File System, NFS, plays a foundational role. NFS allows a system to share directories and files with others over a network. By using NFS, users and programs can access files on remote systems almost as if they were local files. The basic abstraction of a remote file system is via open, close, read, and write. As it comes to naming, the names are location transparent. Location transparency hides the location where in the network the file is stored. The procedure that allows multiple copies of a file to exist in the network is called replication. This improves performance and availability. DFS handles the updates, checks if clients are working on separate copies, and performs reconciliation, linked to learning. Distributed file systems are used worldwide in a range of industries, from banking to healthcare. Read this brief tutorial on distributed file systems and name 2 advantages as well as 2 disadvantages of using DFSs. Flash memory. Flash memory is used for general storage and the transfer of data between computers and other digital products. Many of today's storage devices, such as SSDs, utilize flash memory, which offers considerable performance improvements over traditional mechanical hard disk drives, HDDs. The performance improvements of flash-based storage devices like SSDs come from their ability to access data much faster than mechanical drives. Here SY, no moving parts. Unlike HDDs that use rotating disks and read-write heads, SSDs have no mechanical parts. This not only increases durability, but also means that data can be read from and written to the drive much faster. Random access. Flash memory allows random access to any location on the storage, making it much quicker at reading data that is scattered across the drive. HDDs need to physically move the read-write head to the data location, which takes more time. Faster read and write speeds. SSDs can handle rapid read and write operations. This is especially beneficial for applications that require quick access to large amounts of data, such as video editing, gaming, and high-speed databases. Lower latency. Because they lack a physical read-write head that needs to be positioned, SSDs significantly reduce the time it takes for a storage device to begin transferring data following an I/O request. Improved durability and reliability. With no moving parts to wear out or fail, SSDs are generally more reliable and can better withstand being dropped or subjected to sudden impacts. Lower power consumption. SSDs consume less power, which can contribute to longer battery life in laptops and less energy use in data centers. Global issues in technology. Global distributed file systems. Distributed file systems enable companies that operate globally and handle vast amounts of data from many different sources and in many different ways, such as the following. To store and manage that data in a cloud. To scale up their operations as needed. To enable users across the world to access the data seamlessly. To use encryption and other protection mechanisms to secure sensitive data. To ensure that data is regularly backed up and can be recovered if there's a disaster. Learning objectives. By the end of this section, you will be able to explain how OSs protect computer systems, discuss key security-related functions of the OS, explain how the OS helps the computer system recover from failures, discuss how advances in technology affect the longevity of an OS. Remember that we consider an OS to be reliable if it delivers service without errors or interruptions. In addition to reliability, an OS should provide a high level of protection, security, and stability. Here, we learn about OS protection, security, recovery, and longevity. Protection. The general mechanism that is used throughout the OS for all resources that need to be protected, such as memory, processes, files, devices, CPU time, and network bandwidth, is called protection. The objectives of the protection mechanism are to allow sharing, which in this context means using the hardware to do more than one thing at a time, help detect and contain accidental or unintentional errors, and prevent intentional malicious abuses. The main challenge when it comes to protection is that intentional abuse is much more difficult to eliminate than accidents. There are 3 aspects to a protection mechanism: authentication, authorization, and access enforcement. Authentication identifies a responsible party or principal behind each action. Authorization determines which principals are allowed to perform which actions, and access enforcement controls access using authentication and authorization information. A tiny flaw in any of these areas can compromise the entire protection mechanism. It is extremely difficult to make all these protection mechanism techniques operate in such a way that there are no loopholes that can be exploited by adversaries. Figure 6:36 illustrates the relationship between authentication, authorization, and access enforcement. The diagram shows username John Park, password *** authentication. Are you an authenticated user? Authorization, what are you authorized to do? Access enforcement, what are you accessing? Figure 6:36 The first step of the protection mechanism is authentication, which checks the username and password. Then comes authorization, which checks the privileges, and finally there is access enforcement, which controls access. Attribution, copyright Rice University, OpenStax under CC by 4. 0 license. Security, the process of checking to see if a user's credentials match the credentials in a database of authorized users or in a data authentication server, is called authentication. The traditional means of authentication involves the user providing a password, which is a secret piece of information that is used to establish the identity of a user and should be relatively long and hard to guess. Most systems store the passwords in a password database. A password database must be protected because it is vulnerable most of the time. For example, both organizations and users should avoid storing passwords in a directly readable form. An alternate form of authentication involves using a badge or key. The badge is a logical access system. The badge does not have to be kept secret. It can be counterfeit, but if it is, the owner will know. The badge must be cheap to make but hard to duplicate. Another form of authentication is two-factor authentication, which involves two factors. The system calls or texts a user's phone for the traditional password during login, employing the cell phone as a key. For example, a site sends a text message to a user's phone with a one-time passcode. The user must read the passcode from the phone and type it into the login page. In two-factor authentication, an attacker must have both your password and cell phone to hijack your account. This approach is particularly effective for authenticating to websites, as the requiring of both the password and the physical cell phone is a sufficient deterrent. To enhance efficiency, the two-factor authentication process can be optimized for websites. Once the authentication is completed, a cookie is loaded into your browser. This cookie then transforms your browser into a type of key, granting you the ability to log in with the password as long as the cookie persists. Whenever a user needs to log in from a different browser or different machine, two-factor authentication is used again. After logging in, the user ID is associated with every process executed under that login, because the user ID is stored in the process control block, and children inherit the user ID from their parents. Once authentication is complete, the next step of protection is authorization, the process of determining the relationship between principals, operations, and objects by defining the kind of principals that are allowed to carry out a specific activity with a defined set of objects is called authorization. These principals are represented using a matrix that includes an entry for each principal and a column for each object as a representation of authorization information on given operations. For example, defining who has the authorization to read, view, edit, or delete the file. Each entry in the access matrix describes the capability of each principal over each one of the objects. When the matrix includes all of the principals and all of the assigned objects, it can become complex and hard to manage. The ideal way to solve this problem is to use a guideline such as an access control list. An access control list, ACL, is a set of guidelines that outline the authority of each user, i.e., which user is permitted access to given resources. An ACL controls the access and privileges using a matrix design. The ACL from Oracle features the assignment of users to roles such as basic users, advanced users, customer administrator, among others. A role is configured to confer privileges on objects rather than attaching privileges to individual users, as this would be much more difficult to set up and maintain. The most general form of setting privileges is creating a list of user and privilege pairs, which is called a capability list. A capability list is a list of objects and operations for each user that defines the user rights and capabilities. Typically, capabilities also act as names for objects, which means the list cannot even name objects not referred to in your capability list. For simplicity, users can be organized into groups with a single ACL entry for an entire group, and each group can be made to share the same privileges. While in Windows OS, ACLs are very general, they are relatively simple in Unix Linux. For example, in Unix Linux, access can be read, write, and execute, and it can be granted to the file owner, the file owners group, or the world of all users. In many cases, the user root has full privilege for all of the operations and has access to all of the permissions. For example, the user root can view, edit, and delete a file. ACLs are straightforward and can be utilized by any file systems in Windows. The utilization involves sharing a namespace at a high level of visibility by making it public, while defining another namespace as private, akin to the encapsulation of objects in object-oriented programming. One component of an OS must be in charge of enforcing access rules and safeguarding authentication and authorization to provide a high level of security. The system's access enforcement mechanism has complete authority. Therefore, it must be simple in programming and small in size. The security kernel is a substitute approach that is composed of hardware and software and serves as the OS's inner protection layer. Generally, any kind of management such as memory and interrupt management are provided by a security kernel, linked to learning. Every once in a while, you may get a notification on your computer asking you to update your OS, and the update may include a patch to address a security issue. Often, this security issue is related to a cyber attack that is exploiting some vulnerability in the OS. Check out this tutorial on OS vulnerabilities to gain a deeper sense of the kinds of OS vulnerabilities that these attacks target. Recovery. Like any other system, an OS can crash in the middle of critical sections or while the system is running. These crashes may result in lost data, unexpected results, and inconsistency. For example, if the crash happened before the system had stored a user's information in the main memory, the system will have lost this information. Unexpected results provide the wrong output and may affect other calculations. An inconsistency is a situation that causes the system to produce errors or hardware failure. Inconsistencies may occur when a modification affects multiple blocks. A crash may occur when some of the blocks have been written to disk but not the others. For example, when the system adds a block to a file, it updates the free list to indicate that the block is in use, but if the inode is not yet written to point to the block, this will result in an inconsistency. Another inconsistency can occur when the system, while creating the link to a file to make a new directory entry, refers to an inode, but the reference count has not yet been updated in the inode. The process of resolving OS faults or errors is called recovery. 3 approaches that can address inconsistency issues include check consistency during reboot and repair problem. A good example of checking for inconsistency is the File System Check (FSCK) command implementation for Unix and Unix-like file systems. The system executes FSCK as part of every system boot sequence, so it can check whether the system was shut down correctly or not. If it was properly shut down, it proceeds normally. In the alternative, e.g., crash, power failure, or any other reason, the recovery process will start. The recovery process will scan disk contents, identify inconsistencies, and repair them. The limitations of FSCK are as follows. It will restore disk to consistency, but does not prevent information loss. This loss of information can lead to instability. Also, the FSCK has security issues because a block could migrate from the password file to some other random file, which could make it visible to unauthorized users. In addition, running FSCK may take a long time, and the user will not be able to restart the system until FSCK completes. The recovery process with FSCK will take more time if the disk size is big. Figure 6.37 illustrates an example of the code errors produced from FSCK and the meaning of each code in the Linux OS. A screenshot shows #man FSCK, no errors, 1 file system errors corrected. 2 systems should be rebooted, 4 file system errors left uncorrected, 8 operational error, 16 usage or syntax error, 32 checking cancelled by user request, 128 shared library error. Figure 6. 37 running a recovery process with FSCK resulted in these code errors. The meaning of each code in Linux OS is also given. Attribution, copyright Rice University, OpenStax, under CC by 4. 0 license. Check the order of the rights. This approach avoids some discrepancies by applying changes in a specific write sequence. For instance, to ensure the free list doesn't still contain the file's new block, write the content of the list before adding that block to the file. After ensuring that the list is not including that block, create a reference for the new block in the inode. Using this approach, you'll guarantee that you'll never write a pointer prior to initializing the block to which it points without validation. The validation will force the system to never clear the last pointer prior to setting a new pointer. The advantage of this approach is that it reduces the time spent waiting, as there is no need to wait for FSCK while rebooting. However, there are several drawbacks, such as the potential for resource leaks, e.g., when the system runs FSCK to recover some lost resources. Another drawback is that this approach slows file operation because writing while running the system requires considerable metadata. Perform write-ahead logging. This term is known as journaling file system and refers to the practice of recording the changes in the information in a separate log file, sometimes called a journal file. These changes will be recorded prior to any new change or update on the system. Windows NTFS and Linux X3 implement this kind of log file. The log procedure is analogous to the way log files are used in a database system to enable the correction of updated inconsistencies, which enables the healing quickly in case of any error. Prior to performing any operation, the recovery process will initially store information regarding the operation in a special log file. The next step is to flush the information to the disk before updating any other blocks. For example, a log entry such as, I'll add block 100,101 to a node 313 at index 90, will be added to the system's log, in case the operation involves adding a block to a file. This will guarantee that the actual block modifications can be performed. The system will restore the log in case of any crash to ensure that all of the updates have been saved in the disk. There are many benefits to employing logging, such as reducing the time needed to recover from any failure. Also, improving the ability of localizing logs in the disk will result in improving the system's performance. However, this approach has some drawbacks, namely, the size of the log file will grow over time, and this will affect the system's processing time. This problem can, however, be resolved by performing periodic checkpoints. Longevity. How long does an OS last? Did companies stop developing new OSs? How can the current OS survive? To answer these questions, we need to discuss concepts such as paging, TLBs, disks, storage latency, and multicores as well as virtual machines, VM. Technology and OSs. Many of the basic ideas in OSs were developed 30-50 years ago, when technology was very different. The question is not only whether these ideas will still be relevant in the future, but whether they are relevant even today. After all, technology has changed considerably over the last 30 or so years. For example, CPU speeds went from 15 MHz in 1980 to 2.5+ GHz in 2024, a 167-fold increase. Memory size went from 8 MB to 16+ GB, a 2,000-fold increase. Disk capacity went from 30 MB to 2+ TB, a 6,667-fold increase. Disk transfer rate went from 2 MB sec to 200+ MB sec, a 100-fold increase. Network speeds went from 10 MB/sec to 10+ GB/sec, a 1,000-fold increase. As you can see, there were huge increases in size, speed, and other capabilities. As you may recall, paging is a storage mechanism that allows processes to be retrieved from secondary memory and moved to main memory using pages. In the 1960s, paging originally touted disk speed latency of 80 ms, a data transfer rate of 250 kbs/sec, memory size of 256 KB. Thus, for 64 pages, it took 64 sec to replace all of the memory to address individual page faults and 1 sec to address sequential page faults. Today, we have disk speed latency of 10 ms, a data transfer rate of 150+ MB/sec, and memory size of 64+ GB. For 16 million+ pages, it takes 44+ hours to replace all of memory to address individual page faults, and 320+ sec to address sequential page faults. Therefore, we cannot afford to page something out unless the system is going to be idle for a long time. But the real question is, does paging make sense anymore as a mechanism for the incremental loading of processes? The answer is yes, but by reading the entire binary at once, because 15 MB of binary takes 0.1 sec to read. TLBs have not kept up with memory sizes. 64 entries provide 256 KB coverage. In the mid-1980s, this was a substantial fraction of memory, i.e., 8 MB. Today, TLBs can only cover a tiny fraction of memory. Some TLBs support larger page sizes of 1 MB or 1 GB, but this complicates kernel memory management. Disk capacity has increased faster than access time. Storage access latency for disks is around 10 ms, and it is around 100 microS for flash memory. There are new non-volatile memories, such as Intel's 3D Xpoint, that improve the latency to 100 ns 300 ns. Chip technology improvements allowed processor clock rates to improve rapidly. Unfortunately, however, faster clock rates mean more power dissipation, and now power limitations limit improvements in clock rate. Chip designers are now using technology to put more processors' cores on a chip. In general, all OSs must now be multiprocessor OSs. However, it is not clear how to utilize these cores, and application developers must write parallel programs, which is very hard. Lastly, the current hot trend for OS development is the data center, which coordinates thousands of machines working together, trying to achieve very low latency communication. Link to learning. As nearly every person and business on the planet uses computers today, their reliability and security are increasingly essential. At the same time, there is growing concern about whether the underlying technologies we are relying on to power OSs will become obsolete soon. And there are also questions about what will replace OSs. Check out the debate on what will replace OS and see whether you share any of the concerns. Virtual machines. As you learned earlier in this chapter, a virtual machine is a software emulation of a physical computer that creates an environment that can execute programs and manage operations as if it were a separate physical entity. This emulation allows multiple operating systems that are isolated from each other to run concurrently on a single physical machine. In essence, a VM provides the functionality of a physical computer, including a virtual CPU, memory, hard disk, network interface, and other devices. Recall that the underlying technology enabling VMs is called a hypervisor or virtual machine monitor, VMM. This technology resides either directly on the hardware, Type 1 or bare metal hypervisor, or on top of an operating system, Type 2 or hosted hypervisor. The hypervisor is responsible for allocating physical resources to each VM and ensuring that they remain isolated from each other. This isolation ensures that processes running in one VM do not interfere with those running in another, and thereby enhances security and stability. VMs are widely used for a variety of purposes, including server virtualization, software testing and development, and desktop virtualization. Virtual machines have become a fundamental component of cloud computing, as they allow cloud providers to offer scalable and flexible computing resources to users on a pay-as-you-go basis. Figure 6.38 illustrates the difference between a Type 1 virtual machine monitor and container environment such as via Docker. A container is a standardized unit of software that logically isolates an application, enabling it to run independently of physical resources. A diagram shows notable differences between the virtual machine and containers. It shows virtual machines, VM1 Windows, VM2 Unix, VM3 Linux, hypervisor, infrastructure, V's containers. C1, C2, C3, Docker, OS, infrastructure. Figure 6.38 One notable difference between the virtual machine and containers is that VMs allow for the use of multiple operating systems, whereas containers share a single OS. Attribution, copyright Rice University, OpenStax, under CC BY 4.0 license. When the complete OS is running within a VM, then the system will be called a guest operating system. VMs are heavily used in cloud computing such as Microsoft Azure, Amazon Web Services, Google Cloud Platform, and IBM Cloud. Think it through. VMs versus on-premise computing. VMs on the cloud represent a paradigm shift in how we utilize computing resources, offering compelling advantages over traditional on-premises computing. Cloud-based VMs provide scalability, flexibility, and cost efficiency, making them a promising technology for businesses and individuals alike. In a traditional on-premises setup, a company or user must invest in physical hardware, maintain that hardware, and often over-provision resources to handle peak demand periods. This approach ties up capital and resources in equipment that may quickly become outdated or underutilized. Why are virtual machines on the cloud a promising technology as compared to on-premises use of a computer?